Look, I want to tell you about a number that haunted me my whole career, a number that every good theoretical physicist has written on their wall and stares at. All the great physicists, Dirac, Pauli, Einstein, they all worried about this number. And I am going to tell you right now, with complete honesty, that nobody in the history of physics knows where this number comes from. The number is approximately 1 divided by 137. More precisely, 1 over 137. 35,999. You might say, well, who cares about some random number? What is the big deal about 137? Let me tell you, this number appears whenever light interacts with matter, whenever an electron absorbs a photon, whenever you see anything at all, whenever a chemical reaction happens, whenever your eyes send a signal to your brain. It is the probability, roughly speaking, that a photon and an electron will interact. And it shows up naked, all over the place, in the equations of physics. Now here is the strange part. We can measure this number to incredible precision. We know what it is to about 11 decimal places. That is like measuring the distance from New York to Los Angeles and being accurate to within a single hair. But we cannot derive it from anything. We cannot calculate it from first principles. We do not know why it has the value it has. Is it related to pi, to the base of natural logarithms, to some beautiful mathematical formula? Nobody knows. It is one of the greatest damn mysteries of physics. You might say the hand of God wrote that number, and we do not know how he pushed his pencil. By the end of this lecture, you will understand exactly what this number means, why it matters so much, and why the fact that we cannot explain it reveals something profound about what we do and do not understand about light. You will also learn several other deep mysteries about light that I, personally, despite working on these problems for decades, could never fully answer. And I promise you this, I will not hide behind fancy words. I will not pretend to understand more than I do. I will tell you honestly where we know the answer and where we are completely lost. But before we get into the deep stuff, let me give you some history. Because light has been puzzling people for a very long time, and the puzzles have changed over the centuries. The ancient Greeks thought that light came out of your eyes. They imagined that you shot rays out of your eyeballs, like a flashlight, and when those rays hit an object, you saw it. This is completely wrong, of course. If it were true, you could see in the dark. But it shows that even the question of what light is and how we see has not always been obvious. By the time of Isaac Newton, people understood that light comes from sources like the sun or candles and enters our eyes. Newton did beautiful experiments with prisms, showing that white light is made of all the colors of the rainbow mixed together. He believed that light was made of tiny particles, which he called corpuscles. Then came Thomas Young with his famous two-slit experiment, showing that light makes interference patterns just like water waves. This seemed to prove that light was a wave, not a particle. For about 100 years, the wave theory of light dominated physics. Maxwell showed that light is an electromagnetic wave. Hertz detected radio waves. Everything fit together beautifully. And then, around 1900, things fell apart. Experiments on the photoelectric effect, where light knocks electrons out of metals, did not fit the wave theory. Einstein showed in 1905 that the photoelectric effect made sense if light came in little packets of energy. Particles again. He called them light quanta. We now call them photons. So is light waves or particles? This is the famous wave-particle duality, and it tormented physicists for decades. The answer we arrived at is that light is neither. It is something new, something that has no analogy in everyday experience. It is light. And to understand what that really means, we have to throw out our intuitions and follow the mathematics. Now let us start with something simple, something you have seen 1,000 times but probably never thought deeply about. You are standing in a room at night, and there is a window. You can see the street outside, the cars passing by, maybe some trees, the stars if you are lucky, but you can also see the reflection of the lamp behind you reflected in the glass. The same glass shows you the outside world and also reflects some of the inside light back to you. Now, how can that be? Light is hitting the glass. Some of it goes through, so you see the outside. Some of it bounces back, so you see the reflection. Nothing mysterious about that, right? Wrong. It is deeply mysterious. Let me tell you why. We now know from many experiments that light is made of particles. We call them photons. Each photon carries a certain amount of energy, and that amount depends on the color. Red photons have less energy, blue photons have more, and so on through the spectrum. When the light is very dim, very faint, you can actually count the photons one by one. We have devices called photomultipliers that can detect individual photons. They go click, click, click. Each click is one photon arriving. So here is the puzzle. A single photon comes along and hits the glass. What happens? Well, sometimes it goes through, sometimes it bounces back, but it is always one or the other. The photon does not split in half. You never see half a click in the detector. Either click or no click, full photon or no photon. So I ask you, how does the photon decide? How does it know whether to go through or bounce back? Now you might think, well, maybe there are two kinds of photons. Maybe some are predisposed to go through, and some are predisposed to bounce. Like two kinds of coins, some loaded to land on heads and some loaded to land on tails. Or like two kinds of dice, some loaded to roll high and some loaded to roll low. That sounds reasonable. That would explain it. But it is wrong. And I will prove it to you with a very simple experiment. Suppose we take a piece of glass, plain, ordinary window glass. If you send 100 photons at it, how many bounce back? The answer is about 4. 4% reflection. The other 96 go through. That is a fact you can measure any day of the week with the right equipment. Now, glass has two surfaces, front and back. When light hits the front surface, about 4% bounces. When the remaining light hits the back surface from inside, some of that bounces too. So you might think, okay, total reflection should be about 8%. Front surface contributes 4%. Back surface contributes 4% of the remaining 96%, which is about another 4%. Total about 8%, but it is not 8%. The actual reflection depends on how thick the glass is. If you make the glass thicker, the percentage goes up, then down, then up, then down. It cycles. At certain thicknesses, you get 16% reflection. At other thicknesses, you get 0, nothing, no reflection at all, even though both surfaces are still there. The same two surfaces that should each reflect 4% are together reflecting 0%. Now wait, stop, think about this. A photon hits the front surface. How does it know how thick the glass is behind it? It has not been there yet, and yet it has to make a decision right now at the front surface whether to bounce or go through, and somehow that decision depends on the thickness of the glass which is behind it, which it has not reached yet. Furthermore, if you carefully measure, you will find that with lasers which produce very pure light of a single color, this pattern of 0 and 16% and everything in between continues for very thick glass, more than 50 meters of glass. After millions of wavelengths of travel, the photons still somehow know about that front surface they passed long ago. Isaac Newton, the greatest physicist before the 20th century, puzzled over this for years. He noticed that thin films of oil on water make beautiful rainbow colors. He measured the thickness of soap bubbles. He tried to figure out how the two surfaces of a thin film could affect each other. He could not figure it out. He invented something he called fits of easy reflection and fits of easy transmission. He imagined the photon, or corpuscle as he called it, going through these fits, somehow knowing in advance what it would encounter. Like a person who alternates between being in a good mood and a bad mood, and depending on which mood they're in when they hit the surface, they bounce or go through. It was a desperate attempt to explain something that seemed impossible. Newton, probably the smartest person who ever lived, could not figure out what was going on. And the reason he could not figure it out is that he was missing something fundamental about how nature works. Here is how we explain it now, in quantum electrodynamics. And I must warn you, the explanation is correct, the calculations work to incredible precision, but it does not really satisfy that deep question of how the photon knows. We have merely replaced one mystery with a deeper one, but at least we can calculate now, which is more than Newton could do. The explanation involves something I call little arrows. This is my way of explaining probability amplitudes without the heavy mathematics. We assign an arrow to each way that a photon can get from point A to point B. The arrow has a certain length and a certain direction, like a tiny hand on a stopwatch. Now, suppose a photon can get from a light source to a detector by bouncing off the front surface of the glass. That is one arrow. It can also get there by going through the front surface, bouncing off the back surface, and coming back. That is another arrow. We draw both arrows, and then we add them up tip to tail, like you add vectors in high school physics. The final arrow, the sum of all the little arrows, tells us the probability. You take the final arrow, measure its length, and square that length. That number is the probability that the photon ends up at the detector. Here is the key. Each arrow has a direction that depends on how long it takes the photon to travel that path. The longer the path takes, the more the arrow rotates. It is like a stopwatch that spins around while the photon travels. Imagine a little clock on the photon that keeps spinning at a steady rate determined by the color of the light. So if the glass is thin, the arrow for the back surface reflection has almost the same direction as the arrow for the front surface reflection. The paths take almost the same time. The arrows point nearly the same way. You add them up, get a bigger arrow, more reflection. The probability goes up, but if the glass is thicker, the back surface path takes longer, the stopwatch spins more, the arrow rotates more. At a certain thickness, the back surface arrow points exactly opposite to the front surface arrow. They cancel! Zero reflection, even though both surfaces are still there. The two arrows add up to nothing. Make the glass even thicker, and the back arrow rotates more. Now it points the same way as the front arrow again. They add up. Big arrow, 16% reflection. And the cycle continues as the glass gets thicker. This is what we can calculate. This matches the experiments exactly, to 11 decimal places of accuracy. It is the most precise theory in all of physics. But notice what we are not explaining. We are not explaining how the photon at the front surface knows about the back surface. We are just calculating the probability of various outcomes. We can say what will happen on average over many photons, but not what any single photon will do. And we do not explain why this arrow-adding rule works. It just does. Let me give you an analogy. It is not perfect. No analogy ever is. But it may help you feel the shape of the problem. Imagine a blind archer. She cannot see the target. She does not know where it is. She does not know anything about the field in front of her. But we put many targets out in the field and let her shoot 1,000 arrows. Some arrows hit targets, some miss. Some hit targets in one area, some in another. After we gather all the results, we can draw a probability map. We can say there is a 20% chance her arrow lands in this region, a 5% chance it lands in that region, a 3% chance over there. We have statistics. We have predictions for large numbers of arrows. Now, that map is useful. It predicts what will happen with future arrows, statistically. But it does not tell us how any individual arrow knows where to go. The map is a summary of outcomes, not an explanation of mechanism. We have described what happens without explaining how or why. Quantum electrodynamics is like that. It gives us the map, an incredibly accurate map, a map that works for every experiment we can devise. But it does not tell us the mechanism. And when I say we do not understand quantum mechanics, this is part of what I mean. We know how to calculate. We do not really know what is going on. Here's another way to think about it. Suppose you are driving from Los Angeles to New York. There are two main routes. One goes through the desert, through Arizona and Texas. One goes through the mountains, through Colorado and Kansas. They take different times depending on traffic and weather. If I ask you, which route will you take, you can tell me. You make a choice based on what you know about the routes. Maybe you prefer the desert scenery. Maybe you want to avoid mountain passes in winter. You gather information, you think, you decide. It is a straightforward process. But the photon does something very strange. It is as if the photon takes both routes at once. Or rather, it is as if the probability of the photon arriving in New York depends on what both routes are like, even though the photon can only take one of them. The characteristics of the route it did not take affect the probability that it takes the route it did take. We have a mathematical way of describing this, involving probability, amplitudes, and complex numbers and interference. But we do not have a mental picture of what the photon is doing during its journey. It is neither here nor there. It is not on one route or the other. It is in some strange state that has no analog in everyday life. It is in what we call a superposition of states. Let me stop and make sure you understand what we have so far. Let me explain it the way I would explain it to a bright 12-year-old who asked me a good question. Light is made of little particles called photons. When a photon hits glass, sometimes it bounces, sometimes it goes through. We cannot predict what any one photon will do, but we can calculate the average. We use little arrows that spin like stopwatch hands. The arrows for different paths add up like vectors in mathematics. The length of the final arrow squared gives the probability. Why does this work? We do not know. How does the photon know about all the paths? We do not know. We just know that if you follow this recipe, you get the right answer every single time. And that, believe it or not, is quantum electrodynamics in a nutshell. The calculations can get very complicated, involving many paths and many arrows and many intermediate steps. But the basic idea is exactly this. Arrows add up. Square the result. That is the probability. Now, there's a common misconception I want to destroy. Some people, even some physicists who should know better, will tell you that light is a wave, and that the wave nature of light explains reflection and interference and all these phenomena. This is half true and half nonsense. Let me be very careful here, because this is important. If you have intense light with billions and billions and billions of photons, then yes, the light behaves like a wave. You can use wave equations to predict what happens. Maxwell's equations work beautifully. You can understand reflection and refraction and interference using waves, and it all fits together. This works for many practical purposes, like designing lenses and fiber optics and cameras. But when you turn the light way down, when you count individual photons one at a time, the wave picture breaks down. Each photon arrives as a particle. Click, one photon. Click, another photon. There is no half click. There is no wave spreading out continuously. Just particles arriving one at a time, each carrying a discrete amount of energy. And yet, even with single photons, you get interference patterns. If you run the experiment for a long time, letting thousands of photons arrive one by one, waiting for each one to land before sending the next, the pattern of clicks builds up into an interference pattern, just like waves would make. Bands of light and dark, stripes across the detector. So which is it, wave or particle? The answer is neither. Light is light. It is something that does not fit into the categories our minds evolved to understand. Our brains evolved on the African savanna to track running animals and find ripe fruit, not to understand the nature of light at the quantum level. Light is not like water waves, and it is not like bullets. It is something else entirely. We describe this strange behavior using mathematics. The mathematics works perfectly, but we do not have a good picture in our heads. We cannot visualize what the photon is actually doing between the source and the detector, and maybe we never will. Maybe the universe simply does not work in ways our brains can picture. Let me tell you about an experiment that contains all the mystery of quantum mechanics. It is the famous double-slit experiment, and I used to say that this one experiment has in it the heart of quantum mechanics. In reality, it contains the only mystery. Everything else is just elaboration. Here is the setup. You have a light source on one side. In front of it is a screen with two narrow slits in it, close together, maybe a millimeter apart. Behind that is a detection screen that can record where photons land, maybe a piece of photographic film or an electronic detector. If you block one slit and let photons through the other slit only, you get a simple pattern on the detector. Most photons land right behind the open slit, with the numbers falling off to either side. A blob of hits centered on the slit. Nothing strange. If you block the other slit instead and open the first, same thing. Simple pattern behind that slit. Another blob of hits. Now, what happens if you open both slits at once? You might expect to see the sum of the two patterns. Two overlapping blobs, one behind each slit, adding up to a bigger mess in the middle. That would make sense, right? Wrong. You get something completely different. You get an interference pattern. Bands of light and dark, like zebra stripes. Places where lots of photons arrive, alternating with places where almost no photons arrive at all. Not two blobs, not a smooth distribution, sharp stripes. And here is the thing. There are places on the screen, right in the middle, where you would expect lots of hits, where you get almost nothing. Fewer photons than when only one slit was open. Opening the second slit actually reduces the number of photons landing in certain spots, as if the photons are somehow interfering with each other, canceling each other out. Now here is the really strange part. You can turn the light down until only one photon is in the apparatus at a time. You send photons through one by one, waiting for each one to arrive before sending the next. Each individual photon goes through one slit or the other. It cannot go through both. It is just one particle, one photon, one click. But after you let thousands of photons through, one at a time, the pattern that builds up is still the interference pattern, with bands of light and dark, as if each photon somehow knew about both slits, even though it could only go through one. As if each photon interfered with itself. Wait, you say. Maybe the photon does go through both slits somehow. Maybe it splits and recombines. Maybe it goes through one slit and sends a ghost through the other. Let us put a detector at each slit to see which one the photon went through. Here is what happens. Every time you look, you find the photon goes through exactly one slit. Never both, never half through each. It picks one. Click at this slit or click at that slit. Never both. It is a single particle, all right. But when you add the detectors at the slits, something else happens. The interference pattern disappears. You now get just two blobs, like you expected from the beginning. The stripes are gone. Just two overlapping hills of hits, one behind each slit. So if you watch which slit the photon goes through, it behaves like a particle and the interference is gone. If you do not watch, it behaves like a wave and you get interference. It is as if the photon behaves differently depending on whether we are looking at it. How does the photon know whether you are watching? What is so special about observation? What is so special about having a detector there versus not having one? I do not know. Nobody knows. This is the measurement problem. The mystery at the heart of quantum mechanics, and we have been arguing about it for more than 50 years, without resolution. Some physicists say the wave function collapses when you measure. Some say the universe splits into multiple branches. Some say there is no real problem, just a mismatch between our intuitions and reality. There are at least a dozen interpretations of quantum mechanics, and none of them have been experimentally distinguished from the others. They all give the same predictions. They just tell different stories about what is really happening. But wait, it gets even stranger. There is something called the delayed choice experiment. You can set it up so that you decide whether to observe which slit the photon went through after the photon has already passed the slits. And it still works. If you choose to look, the interference pattern disappears. If you choose not to look, it appears, even though the photon has already passed through the slits by the time you make your choice. It is as if the photon goes back in time and changes its behavior based on what you will do in the future. Of course, that cannot really be what is happening. There is no information traveling backward in time, but trying to understand what is happening makes your head hurt. And then there is entanglement. You can create pairs of photons that are correlated in strange ways. Measure one photon here, and you instantly affect what you will find when you measure the other photon over there, even if over there is on the other side of the galaxy. Einstein called this spooky action at a distance, and he never liked it. But experiments have confirmed it is real. The correlations are there, just as quantum mechanics predicts. None of this violates causality or allows faster-than-light communication. The correlations are real, but you cannot use them to send messages. But it tells us something very strange about reality. Things are more connected than we thought. The universe is not just a collection of separate objects doing their own thing. There are holistic features that you only see when you look at the relationships between things. Let me walk you through another thought experiment, step by step. This one reveals something surprising about how light reflects from mirrors, and it connects back to those little arrows I told you about. You have a light source on one side and a detector on the other side, at the same height. In between is a flat mirror lying horizontally below them. The light from the source bounces off the mirror and hits the detector. Simple enough. Now, you were taught in school that the angle of incidence equals the angle of reflection. Light comes in at some angle, bounces, and leaves at the same angle on the other side. So only the middle part of the mirror matters. Light from the source hits the middle, bounces at equal angles, and reaches the detector. The parts of the mirror way off to the side, at the edges, do not contribute. The ends of the mirror, far from the middle, have as much to do with the reflection as with the price of cheese, right? They are irrelevant. But in quantum electrodynamics, we have to consider all paths. A photon could, in principle, go from the source to the far left edge of the mirror, bounce, and travel to the detector. It is a longer path, a crazy path, but it is a possible path. We have to include its arrow in the calculation. Similarly for the far right edge. And every point in between, every spot on the mirror gives a possible path. We draw an arrow for each path, all the same length, but with directions depending on how long the path takes. Here is what saves us. The paths from the edges take much longer than the paths from the middle. The arrows for these edge paths point in all different directions, spinning around like crazy as you move along the mirror. And when you add up a bunch of arrows pointing in random directions, they cancel out. They form a spiral that curls up tightly and goes nowhere. The contributions from the edges add up to nearly zero. The contributions from the middle add up nicely because the paths are all about the same length. The arrows all point in nearly the same direction. They reinforce each other. They add up to a substantial final arrow. So we get the right answer. The middle of the mirror is what matters for reflection. But we got this answer by including every possible path, even the crazy ones, and then adding up the arrows. Nature does the same thing, in some sense. All paths contribute, but most of them cancel. Now here is a fun trick. Suppose you want to use those edge parts of the mirror after all. You can! You scratch tiny grooves in the mirror at the edges, spaced exactly right. These grooves block certain paths and let others through. They eliminate half the arrows, the ones that were pointing the wrong way and causing cancellation. With the spacing just right, the remaining arrows from the edge all line up instead of canceling. They reinforce each other. What happens? Light reflects from the edge of the mirror at an angle that should be impossible according to the simple rule of angle equals angle. This is called a diffraction grating, and it is how CDs work. Those rainbow colors you see on a CD come from light reflecting at impossible angles, thanks to the tiny grooves in the surface. We are exploiting those forbidden edge paths by cleverly controlling which ones contribute to the total. Now I want to come back to that mysterious number, 137, or rather 1 over 137, which is approximately 0.00729. This number has a more technical name. It is called the fine structure constant, and physicists usually denote it with the Greek letter alpha. It was discovered in the early days of quantum mechanics when people were studying the fine details of atomic spectra, the precise wavelengths of light that atoms emit and absorb. What does it mean physically? It is the probability, roughly speaking, that an electron will emit or absorb a photon. More precisely, it determines the strength of the electromagnetic interaction. How strongly does light couple to matter? How strongly do electric charges interact with electromagnetic fields? That is what alpha tells us. In the little arrows I told you about, alpha appears as the basic building block. Every time an electron interacts with a photon in a Feynman diagram, you multiply by the square root of alpha. This makes each interaction have a probability proportional to alpha, which is about 1 over 137. Small, but not too small. Just right for making atoms work. Now, here is what makes this number so special. It is dimensionless. It has no units. It is just a pure number, like pi or the golden ratio or the number e. Think about that. The speed of light is 300,000 kilometers per second, but that number depends on your choice of units. In miles per hour, it is about 670 million. In furlongs per fortnight, it is something completely different. The number changes depending on what units you use. But alpha is always 1 over 137, no matter what units you use. Aliens on another planet, using their own units for charge and speed and energy and distance, would get the same number. It is a fundamental property of nature, not an artifact of human conventions. It is a pure number that nature chose. Even stranger, alpha is made from a combination of other fundamental constants. It is the electron charge squared divided by Planck's constant times the speed of light, with some factors involving the permittivity of empty space. It combines electromagnetism, quantum mechanics, and relativity into one number, 3 great pillars of physics, all connected by this one mysterious constant. This is remarkable, and we have no idea why it has the value it has. Paul Dirac, one of the founders of quantum mechanics, called it the most fundamental unsolved problem in physics. Wolfgang Pauli, another giant of quantum theory, said that when he died, his first question to the devil would be about the meaning of the fine structure constant. Some say he was joking. I am not so sure. Leon Lederman, who discovered several subatomic particles and directed Fermilab, loved this number so much that he put the address 137 on his house. Physicists take this seriously. For years, physicists tried to derive this number from pure mathematics. Maybe alpha equals pi divided by some power of 2. Maybe it involves e, the base of natural logarithms. Maybe some clever combination of mathematical constants gives exactly 137. Every attempt failed. As the measurements got more precise, every proposed formula was ruled out. The number 137 is not exact. It is 137.035999, and the decimals go on. Every simple formula people proposed gave the wrong digits somewhere after the decimal point. The number seems to be neither a simple mathematical constant nor derivable from any known principles. It is just what it is. We measure it and put it in our equations. In our current understanding, we just have to measure it. We put the measured value into our equations, and then the equations work brilliantly. But we cannot predict what the value should be. We cannot explain why nature chose 1 over 137 instead of 1 over 100 or 1 over 200 or 1 over 50 or any other number. And here's the disturbing part. If alpha were different, the universe would be very different. If it were larger, electrons would be held more tightly to nuclei, atoms would be smaller. Chemical reactions would work differently. The chemistry of life might not work at all. If alpha were much larger, say around 1/10 or bigger, atoms might not exist at all. Electrons would fall into nuclei. Matter as we know it would not form. If alpha were smaller, say around 1 over 1,000, matter would be loosely held together. Chemistry would be different again. Stars might not work the way they do. Fusion might not happen in the right way to produce carbon and oxygen. Some people find this suggestive. The universe seems fine-tuned for complexity in life. Change a few constants like alpha, and you get a boring universe with no interesting chemistry, no planets, no biology. Is this a coincidence? Does it hint at something deeper? Some people invoke the anthropic principle. Others invoke a multiverse where different universes have different constants, and we happen to be in one that allows observers to exist. I do not know the answer. It is one of those deep questions where we are still groping in the dark. Let me tell you about some of the strange ideas people have had about 137. Arthur Eddington, a brilliant astrophysicist who helped confirm Einstein's general relativity, became convinced that 137 could be derived from pure logic. He thought all the constants of nature were logically necessary, not contingent facts. He spent years trying to prove this, and he kept getting different answers as the measurements of alpha got more precise. He would adjust his theory to match the new measurements. When he died, he had not succeeded. Werner Heisenberg, who invented the uncertainty principle, also tried. He thought maybe there was a maximum speed, a minimum length, a smallest action, and from these fundamental limits you could derive all the constants. He did not succeed either. Wolfgang Pauli became almost mystically obsessed with 137. He noticed that 137 is related to the golden angle in some way. He noticed connections to Jewish mysticism, where certain numbers have special significance. He died in room 137 of a hospital in Zurich. Some say this was coincidence. Pauli might have appreciated the irony. The truth is, as far as we know, 137 has no special mathematical significance. It is not pi divided by anything. It is not e to any power. It is not the golden ratio in disguise. It is just a number that nature happens to use, and we do not know why. Now, you might be getting frustrated. You might say, Feynman, you keep telling us things we do not know. You told us we do not know how the photon decides to reflect. We do not know why the double-slit experiment works the way it does. We do not know where the fine structure constant comes from. We do not know what observation means in quantum mechanics. Is there anything we do know? Yes, we know how to calculate. We know the rules of the game with extraordinary precision. We can predict with incredible accuracy what will happen in any experiment involving light and matter. Quantum electrodynamics gives predictions that match measurements to 11 decimal places. That is like predicting the distance from here to the moon and getting it right to within a single human hair. It is the most accurate theory in the history of science. So the theory works. We can do physics with it. We can design lasers that read CDs and DVDs. We can build semiconductors that run computers. We can make LEDs and solar cells. We can manipulate light and matter at the quantum level. All of this technology flows from quantum electrodynamics. But when you ask why, that is a different question. Physics tells you how nature behaves. It gives you rules you can use to predict experiments. it does not always tell you why nature chose to behave that way. Think about it this way. You ask me, why do magnets attract and repel? I tell you about magnetic fields and field lines. You ask, why are there magnetic fields? I tell you about electric charges in motion creating magnetic effects. You ask, why do charges create magnetic effects? I tell you about the electromagnetic force and Maxwell's equations. You ask, why is there an electromagnetic force? And at some point I have to say, because that is the way nature is. At the bottom of every chain of why questions, there is a brute fact, something we observe but cannot derive from anything deeper. That is just how nature is. With light, we have reached that bottom in several places. Why is alpha equal to 1 over 137? We do not know. How does the photon know which slit you are watching? We do not know. Why do the arrows add up in this peculiar way? We do not know. These might be the rock bottom of physics, or they might be waiting for a deeper explanation. These are not failures of intelligence or effort. Many brilliant people have worked on these questions for decades. The questions may simply be unanswerable in the way we are asking them. Or they may be waiting for some future revolution in physics that we cannot yet imagine. Someone may come along with a completely new way of thinking that explains these mysteries, or we may never know. Let me tell you one more strange thing about light, and then I will try to put it all together. Light, it seems, always takes the path of least time. When light goes from point A to point B, it travels along the route that gets it there fastest. This is called Fermat's principle, named after the mathematician Pierre de Fermat, and it was known centuries ago. In a vacuum, the fastest path is a straight line. And sure enough, light travels in straight lines in empty space. When light enters glass or water, it slows down. Light travels slower in glass than in air, and light bends at the boundary in exactly the way that minimizes the total travel time. A little more time in the fast medium, a little less time in the slow medium. The angles work out to minimize the total time. This explains Snell's law of refraction. Now, wait a minute. The light has to get from A to B, but it has not been to B yet. How does it know which path takes the least time? It would have to try all the paths first, measure the times, and then pick the shortest one. But that is absurd. That requires knowing the future. How can it know the future? Here is where the arrow picture helps again. In quantum electrodynamics, the photon does not just take one path. We consider all paths from A to B, draw an arrow for each, and add them up. It turns out that for paths near the shortest path, the arrows all point in about the same direction. They add up constructively. The paths nearby have almost the same travel time, so the arrows are nearly parallel. For paths far from the shortest path, the travel times are all different. The arrows point in random directions and cancel out. They spiral around and add up to nearly nothing. So the photon does not know the future. It does not magically pick the shortest path. Rather, all paths contribute, but the ones that contribute most are the ones near the shortest path, because only those have arrows that reinforce each other. The math works out so that the classical rule, the path of least time, emerges from the quantum calculation. This is actually a general principle in physics. It is called the principle of least action. The path nature takes is the one where small changes in the path do not change the action very much. The action is a mathematical quantity related to energy and time. Near the path of least action, all the nearby paths have almost the same action, so the arrows line up. Away from it, the paths have very different actions, and the arrows cancel. I find this beautiful and mysterious. Nature behaves as if it is exploring all possibilities at once, and the consistent possibilities, the ones that reinforce each other, are the ones we observe. It is a very different picture from particles following trajectories like billiard balls bouncing around a table. The billiard balls do not explore all paths. They just follow one path, determined by forces acting moment by moment. But quantum particles are somehow aware of all the possibilities. So what does all this mean? What have we really learned about light? First, light is fundamentally strange. It is not waves in the classical sense, and it is not particles in the classical sense. It is something new, something without analog in everyday experience. We can calculate its behavior with incredible precision, but we cannot visualize what it is actually doing. We cannot form a mental picture that is both accurate and intuitive. Second, nature is probabilistic at its core. We cannot predict what any one photon will do. We can only calculate probabilities. This is not a limitation of our knowledge or our instruments. It is not that we are missing some hidden information. As far as we can tell, this is how nature actually works. The universe is not deterministic at the quantum level. There is genuine randomness built into the fabric of reality. Third, there are deep mysteries we have not solved. The fine structure constant, the role of measurement, the mechanism behind quantum behavior, these are not just gaps in our knowledge, they are fundamental puzzles that may require entirely new ways of thinking. They have resisted solution for decades, despite the efforts of the best minds in physics. Fourth, despite the mysteries, we have achieved something remarkable. We have a theory, quantum electrodynamics, that predicts the behavior of light and matter with extraordinary precision. Whatever light really is, we know how it behaves. We can engineer with it. We can manipulate it. We have harnessed it for technology. The fact that we do not understand it at the deepest level does not stop us from using it. This combination of understanding and mystery is, I think, what makes physics so wonderful. We are not at the end of knowledge. We are in the middle of a great adventure. We have learned an enormous amount, and there is an enormous amount still to learn. That number, 1/137, is a humbling reminder. We understand so much about how light works. We can calculate, predict, build technologies, win Nobel Prizes. But at the deepest level, when we ask where the rules come from, we are still in the dark. The most important question about light, the question of why it couples to matter with exactly this strength, remains unanswered. Maybe someday a young physicist, perhaps one watching this lecture, will figure it out. Maybe they will discover a deeper principle from which alpha can be derived. Maybe they will finally answer the question Newton could not answer, and Dirac could not answer, and Pauli could not answer, and I could not answer either. Until then, we keep working, we keep asking questions, we keep following the evidence wherever it leads. That is what science is. Not a collection of answers, but a method for seeking truth. Not certainty, but a willingness to live with uncertainty while striving to reduce it. Not dogma, but a constant questioning that never ends. You know, people sometimes ask me if I am frustrated that we do not understand everything. If it bothers me that after decades of work, there are still these deep mysteries. And I always say no. I would be terribly bored if we understood everything. Where would be the fun in that? The joy of physics is not in having all the answers. It is in the chase. It is in that moment when you see something you did not expect. It is in the late nights, scribbling on paper, trying to figure out why the experiment gave that strange result. It is in arguing with colleagues about what the equations really mean. And light, this thing we take for granted every day, this stuff that enters our eyes and shows us the world, this apparently simple phenomenon, turns out to be one of the deepest mysteries in all of nature. How wonderful is that? How lucky we are to live in a universe strange enough to surprise us. I want to leave you with a thought. You might feel troubled that there are things in physics we do not understand. You might wish I could wrap everything up in a neat package, explain it all make perfect sense. But I think the mystery is a good thing. It means there is more to discover. It means physics is not finished. It means a young person today can still make contributions that fundamentally change our understanding of the universe. The frontier is not closed. The territory is not all mapped. The question of why light behaves as it does, why the fine structure constant has its peculiar value, why quantum mechanics works the way it works, these questions are waiting for answers. Maybe impossible answers, or maybe answers that are just around the corner. Maybe it will take a revolution as big as quantum mechanics itself, or maybe we will never know. Either way, is it not wonderful that we can ask such deep questions, that we can probe the nature of light, that strange thing that fills our eyes with color and our world with beauty, that we can reason our way to conclusions that no one could have imagined a century ago? I think it is the most wonderful thing in the world, and I hope you do too. Now, I have talked for a long time, and I am curious what you think. Let me ask you this. If you could change the fine structure constant to any value you wanted, what would you change it to, and why? What kind of universe would you create? Think about it. I would love to know your answer.